Hi, I'm Nick. I work for a company called Emnify. I'd like to use a cute example to explain what we are doing. We have a customer that makes smart mouse traps. Once a mouse is trapped, a push notification is sent. The mouse trap is always online and it doesn't depend on your Wi-Fi for connectivity because it has Emnify SIM inside. We don't offer voice, only data. Shipping IP packets is an important part of our business. We relied on DPDK in the past, but now we are transitioning to eBPF. Today, I want to tell you why we see eBPF as a game changer. I'd like to acknowledge that signaling in cellular networks is a complex topic. I will conveniently ignore signaling today. Once a device is online and authenticated, the data path is rather simple. It is a GTP tunnel we have to terminate. On the right-hand side, we have AWS integration. Device traffic gets right into the customer's VPC without traveling over the public internet. Actually, it enters our VPC first. The traffic is wrapped in GRE because AWS Transit Gateway understands GRE and it can match a tunnel to the customer's VPC we are peering with. We had to convert between GTP tunnels on the left-hand side and GRE on the right-hand side. We have over 1 million GTP tunnels in a busy region, but relatively few GRE tunnels. Clearly, you can't have a million tunnels in Linux. Instead, a single tunnel in so-called collect mode aggregates all GTP traffic. A TC program uses BPF SKB get tunnel key helper to recover information about a tunnel. The program uses BPF maps to match a tunnel to the customer and to find out the target GRE tunnel. Finally, the program updates the tunnel key and redirects the packet into a GRE device, also operating in collect mode. It's reasonably fast. Better yet, it handles all complex corner cases, such as packet reassembly and fragmentation and sending ICMP fragmentation needed messages. Corner cases do happen, but for the majority of packets, conversion between GTP and GRE is as simple as changing a few headers in the packet buffer. We use XDP program for the fast path. It matches a tunnel to the customer and finds out the target GRE tunnel using eBPF maps shared with TC program. So apparently, eBPF is quite handy and powerful. However, we consider it a breakthrough for a different reason. Let's have a look at the broader picture. There are some complications. On the left, a device can open several sessions simultaneously. It results in multiple GTP tunnels to be used for different traffic classes. On the right, it is typically a few GRE tunnels per customer for improved throughput and redundancy. Some customers do their own tunneling so that packets can carry additional metadata, such as an endpoint ID. And in between, we have a NAT and a firewall and flow logs and a kitchen sink. Due to overall complexity, we prefer to do several apps instead of a single monolith. So we have multiple apps to operate, and not just multiple apps, but multiple instances of every app. It would be nice if we could run several apps side by side on a single server. Another challenge is state. Product evolves and requirements change, therefore we have to push updates often. But the tunnel might live for days. Either we keep old versions of the software around until it drains, or we impact customers. It would be nice if we could extract state out of a running instance and somehow inject it into a new one. With eBPF, it is finally possible to run multiple packet processing apps side by side. That's why we write our applications in eBPF, or more precisely, the packet processing part. We use Golang for user space part. We are happy Cilium eBPF users. We manage our fleet with Kubernetes. I have to acknowledge that eBPF maps are accidentally awesome. They are equipped with powerful API to populate and to read back the content. Speaking of content, a complete type information is available. It is not opaque bytes you are looking at, but rather structures with named fields of known type. It is possible to build a generic tool to dump and restore state, performing conversion if that data layout changed. With sufficient effort, streaming replication can be achieved. We can also populate a eBPF map from a database table in a generic way. I'd love to dedicate more time to eBPF maps, but unfortunately I can't. Speaking about high-performance packet processing, it's hard to ignore DPDK. It has been around for a while and it is quite popular. The idea is to remove a network interface from the kernel and to drive it from user space. Packet buffers are shared with user space via memory mapping. Similarly, receive and transmit links are exposed. Application pulls receiving in a busy loop to find out if there is an incoming packet. I have to acknowledge that DPDK in general is faster than Ebpf. A modern CPU has many special-purpose instructions, such as AVX, which Ebpf lacks. When using DPDK, a CPU core is typically dedicated to a single task. Hence, CPU cache hit rates are higher. DPDK is also more flexible since it is just regular user space. However, DPDK means busy polling. As soon as there are more threads than CPU cores, everything falls apart. With Ebpf, it is possible to run multiple packet processing apps side by side easily, and it is huge. Finally, let's talk about running in Kubernetes. An application relying on XDP works just fine in Kubernetes, except it doesn't. An XDP program won't see any packets coming in. It doesn't work with virtual internet pairs. It probably doesn't work with Netkit either. Let's follow the path of an incoming packet. A TC program attached to ETH0 observes a packet and redirects it into VF1. Normally, a redirect would put a packet on an internal queue inside virtual Ethernet pair, and packet processing would end. Eventually, the kernel will find out that there is a packet pending. The packet will re-emerge from VF2, passing through SDP and TC layers as expected. But there is an important optimization happening. Instead of a plain redirect, BPF redirect peer is done. The packet doesn't go into a queue. The packet processing doesn't end. Instead, it performs another iteration with ingress interface set to VS2. Since there is no waiting on the queue, the latency improves. Several corners are cut and XDP is skipped. However, for our packet processing needs, we actually want the packet to get on a queue. Consider this. We have many packet processing apps, each with their own Ebpf blobs. Accumulating multiple packets and processing the batch together is more effective from CPU cache perspective. We'd also like to dispatch packets to pods in XDP, since going through TC to hit XDP makes little sense. Apparently, packet processing apps have different needs compared to regular container workloads. Since we don't see a way to unify conflicting requirements, we provision a secondary interface with a custom CNI. It's time for a conclusion. We are taking smart devices online using XDP and TC. The service is complex, therefore we are doing several apps instead of a monolith. With the BPF, it is finally possible to run multiple packet processing apps side by side. It is really cool. However, to make it work in Kubernetes, a proposed build CNI is necessary. We are currently working on one.